Alright guys, we're going to do 5.2b today, which is integrating other trig functions. And basically what it kind of entails is more antiderivatives where you got to use u substitution. And some of them turn out to be natural log problems and some of them don't. It's just you can't really identify it until you try it. So we're going to be looking at some kind of weird integrals today. And you got yesterday, we made a big master list of all the integrals and derivatives that you need to memorize. But there's a lot of antiderivatives not on that list. So like for example, if I gave you the integral of tangent of x dx as our first example here. Integral of tangent is not memorized. The derivative of tangent, we've memorized that as secant squared, but the antiderivative of tangent is not a memorized one. So if I ask you what is this equaled, it's not memorized. We know that for a fact. So we need to figure out what's the antiderivative of tangent. And to do that, I'm going to rearrange tangent of x. I'm going to actually call it sine over cosine. So integral of sine of x over cosine of x. Just using a basic trig property here to rewrite it. Then I'm going to attempt to do some u substitution to this thing. So my first step is I'm going to let u equal, how about cosine of x? And according to u substitution, I take my derivative, du dx. And the derivative of cosine is negative sine of x. And you're going to multiply your dx over it and get du equals negative sine of x dx. And so you look at our problem, and you know, with these u substitution problems, we're rewriting things. So the sine of x dx is right there. We don't need the negative sign, so I'm going to flip it over to the du here. Negative du equals positive sine of x. Switch the signs. So we rewrite this integral. We now have the integral of a fraction. On top, it turns into negative du, and on bottom we have u. So we have negative du over u, which if I was to rewrite this, I could pull the negative sign out in front and just say 1 over u du. And now I see, oh yeah, it's a natural log problem. So rewrite this thing as negative natural log absolute value of u, and since there's no bounds, I'll put a little plus c on there. And so I'm going to change my u back. I'm going to switch back to, remember u was cosine. So I'm going to have negative natural log absolute value of cosine of x, and then I'll put a little plus c. And there's my answer. So u substitution with tangent of x. You could do the same thing if you had the integral of like cotangent. You could change it into cosine over sine and try u substitution. So that's definitely one example I wanted to show you guys today. There's a couple of others I'm going to show you that actually get a little more strange than this one. The next example, you would never know to solve this way unless somebody showed you first. It's the integral of secant, which is another one we don't have memorized. Secant tangent, we know that goes back to secant, but the integral of secant's not on our DNI list if you look at that list we made yesterday. So this one's going to be a really strange one to solve. In fact, I'm going to do something that you would really never think of until someone showed you. I'm going to take this integral, rewrite it as the integral of secant of x, and then I'm going to times the whole thing by 1. So I'm going to times it by 1, and this 1 is going to be in a fraction that's going to be a little bit stranger. So I'm going to make this big parenthesis here. And the fraction I'm going to use is secant of x plus tangent of x. And I'm going to do the same thing on the bottom. Secant of x plus tangent of x. I told you you would never think to do this, but basically all I'm doing is multiplying by 1. So this is a times 1 that I have going on here. So I'm not changing the integral whatsoever. All of this crosses out and cancels and goes away. But the reason I'm going to do this is because I'm going to try and make this problem a little more solvable. And the way I'm going to do it is I'm going to take secant and distribute it in. So I'm going to rewrite this integral. Now it's one big fraction, and on top I have secant times secant. So secant squared of x plus secant times tangent. Secant of x times tangent of x. And then on the bottom I have secant plus tangent. So secant of x plus tangent of x dx. And then to solve this, I'm going to try u substitution. So let u equal something. I'm going to let u equal the bottom, secant of x plus tangent of x. And I'm going to find du dx, the derivative. And the derivative of secant, we all know, is secant of x, tangent of x. Plus, the derivative of tangent is secant squared. So you can see why I did this. Secant tangent plus secant squared is exactly what we have on top of this fraction. Secant squared plus tangent of x. So all of this is what I was going for. Who would have known, right? So multiply the dx over, and du equals all of this. So my new rewritten integral, sorry for the background noise, hopefully it's not too bad, but is going to look like this. My new rewritten integral, the entire top piece becomes du, and everything on the bottom was u. And if you really want to rearrange it, it's integral 1 over u du. Completely a natural log problem that you would never see. So now I know my answer is natural log, absolute value of u, plus c. But I'm going to rearrange, put the u back in there. Natural log, absolute value. Remember what u was? It's right up here. It's secant of x plus tangent of x. So secant of x plus tangent of x. And then I'll put my little plus c on the end. And that is my answer. So it all makes, perfect sense, so to speak, when you see it starting here. But to know that you had to do that first step times this weird fraction by secant, you really wouldn't know to do that until somebody starts showing you some of these. Somebody had to sit around for a few days to try and figure out how to do this integral. They had to get really creative with how can I rewrite it and use u substitution. So this is a pretty creative way to kind of come across it. So it's an odd one. Definitely a good one to write down for the notes. And then another really odd one I was going to show you is cosecant. Cosecant's kind of a strange one here. If I asked you to find our next example, the integral of cosecant of x dx. Again, not on our D&I memorized list. So it's not memorized. I want to solve it. It's going to be really hard to solve unless I use a trig identity. A trig identity that the chances of remembering this is kind of slim. So trig identity. I'll make my little thought bubble here. And I'm going to use this trig identity. Cosecant of x is actually equal to the secant of pi over 2 minus x. If you look up that trig identity, cheat sheet I gave you, or you were to look inside your textbook or something like that and look at all the trig identities, those big lists, this is one of them. It's called a cofunction identity. So it's a cofunction identity. And so cofunction identities, I doubt you're going to have this one memorized. I don't have this one memorized. I have to look it back up to remember it. But I'm going to apply it to this problem. I'm going to rewrite this integral as the integral of secant of pi over 2 minus x dx. And then I'm going to use u substitution. And I'm going to let u equal pi over 2 minus x. And the reason is the derivative du dx is actually just going to be -1. The derivative of pi over 2 is a number, and a number derives to 0. And negative x becomes -1. So I'll move this over and say du equals negative dx. And in my problem, I don't need a negative, I need a positive dx, so I'll switch the signs here. Negative du equals dx. So all I'm rewriting is this, changing the dx into a negative du. And my new integral is integral secant of u times negative du. So I'll put the du here, and I'll put the negative sign, how about out in front of the integral? It's more convenient there. And the reason I did all this work is secant, well, we just solved for secant. Wasn't that in the last example? We did all that work for integral of secant. Remember, I'll put it back on the screen for a second. This is what we ended up getting. We did all that work in the last example and got secant was natural log secant of x plus tangent of x plus c. So I'm just going to go straight to this. I'm going to write a little note for the notes here. Solved in the last example. And since I solved it in the last example, I'm going to take this answer and say the final answer is going to be a negative natural log absolute value, and then we'll change it to secant of u plus tangent of u plus c. That's going to be, using that last example, it turns into secant plus tangent. So let's change the u's back. Negative natural log absolute value of secant, and the u is going to switch back into pi over 2 minus x plus tangent of pi over 2 minus x plus c, which is totally a great answer. We could circle it. If you wanted to change your answer up, you're going to notice in textbooks they will use more co-function identities. So another thought bubble here. Co-function identities to rewrite this. I'll just put identities like that. We can actually change it so that it's negative natural log absolute value. Secant of pi over 2 minus x, remember that's the same thing as cosecant of x, according to this identity. And then plus tangent of pi over 2 minus x. This thing, if you look at your co-identities, is the exact same thing as cotangent of x plus c. And you could say this is your final answer. Mathematically, the two circled answers are the exact same thing. I've just kind of rearranged them. So these trig problems with the u substitution, they're the oddball ones today. They're the ones that you have to use a strategy you would not really think of. This last example, we had to use a co-function identity. We'd have to kind of go look this up and remember it. The example before that, we had to multiply the entire integral by a really strange fraction. It's just the number 1, but in a really weird fraction form. Or the first example, which is now looking pretty easy compared to these other two, we just took tangent and changed it into sine over cosine, basically. So what you really want to do is just write down the 4 equations that you can see on the screen now, the 4 different integrals that we just got done solving. And you can either remember the process and remember how to solve them by hand, or I always find it easier, these might be the ones that you just want to commit to memory. We've got tangent, cotangent, you can see them on the screen there, secant and cosecant. So either you're going to memorize the 4 integrals, or you're going to have to remember the process and how to solve them by hand each time. It's probably easier just to memorize them. I recommend you add them to your master list of memorized integrals and derivatives and just start working on them. I know they're not the easiest of ones. So yeah, hope this helps, and I'll see you guys all in class.